Why is differentiation or derivatives important? The reason is quite simple. The derivative is the mathematical expression of change, and the change, how a system changes in time, is often essential to know something about when we model a physical phenomenon. If we know the state of a system and we know the laws of change, we can, in principle, compute the states of the system in all future time. Regrettably, differentiation of continuous function is a bit tricky to do on a computer. And this is why we replace the function with differences. The idea is quite general, and every time we use a discrete representation of a function, the differentiation becomes differences, or rather finite differences, as we usually say. The mathematical definition of differentiation reads: you have an f as a function of f that you want to differentiate. You take the limit as some tiny value epsilon goes to 0, an infinitesimal size, and you compute the following fraction. The function value at some slightly higher value than x minus the same function value at x divided by this tiny value. I hope you have seen this expression many times, but have you really understood what it means? Or does it have any practical value? As we shall see, it does. So say that we are not going towards the limit of the infinitesimally small epsilon. We are simply saying that it's just some tiny value, right? So now we'll do the approximately equal to, and everything will keep just as it is. Even with this simplified formula, we will get a good approximation of the derivative. So what I want you to notice now that is this approximation on the right-hand side of the equal sign is a finite difference. And what we usually do is we rewrite this. Instead of epsilon, we use age, which is similar to what we did before. So the age is now some finite step size. So exactly the same, we have just replaced epsilon with age. So in order to have a feeling for how good this approximation is, we will explore an example together. Consider, if you will, the sine function and its associated derivative, which is the cosine function, like so. So if we set x equal to 1, the derivative of the sine function, so let me say that our function is the sine function, and the derivatives evaluated at 1 will be the cosine function of 1, which is approximately not equal to, approximately 0.54. Now let's use our formula for the derivative for the same computation. So we want to compute the derivative of f, the sine function, at 1. So we simply insert the expression, and let's say age is equal to 100 plus 100 divided by 100. And then we have to subtract f of 1. So this will be sine of 1.01 minus sine of 1, and we divide by 0.01, and if we compute this we will get something like 0.536. And now what I want you to notice is that these two values are not that far from each other. It's pretty close. So let's look at a programming example. Alright, so now we'll do the same thing that we just did analytically in Python. We need to import numpy as np, and because we want to have some command line arguments, we'll import sys. Alright, and at first we'll simply define the function for the derivative. We call it diff. It will take a function x age. Yep, that's a point, and a small psi number age, and we'll simply return f x plus age minus f of x, and if you remember what it is we divide by age, but we'll specify that this is a float, so we'll be sure it's correct. And I do this because in Python 2 this will be you have some problem with this integer division things, whatever. I'm using Python 3. So the x will be an input argument or a command line argument, sysargv of 1, and age equal eval sys.v arg the second argument. All right. And then we'll compute the approximate derivative, which will be, and we'll simply pass in the sine function, an x and an age to our diff function up here. All right. And then we will compute the exact derivative, which is the cosine of x. And then we'll print the approximated value is approx deriv, and print the exact value is exact. And lastly, we'll compute the error is, which is exact value minus the exact derivative. And then we'll be able to kind of gauge how good this function is depending on the size of our age. All right, so let's go to the terminal. Python Discrete 2 is this program, that's what I called it anyway. And we need an x number and our step size 0.1. And we'll see how that does. Oh, whoops. So this is supposed to be the exact deriv and the approx. There, let's try it again. There we go. Let me see the, so yeah, we're close, in the neighborhood. So let's decrease the step size and see if it gets better. And it does. And we can keep going like this. Yeah, great. A nice little programming example. Frequently, we will need the finite different approximation of a derivative to a discrete function which is defined on the mesh, and like I went through in the previous video in this little mini series. So say we have some x's and some corresponding function values on that grid. So what we do now is we compute an approximation of the derivative as a finite difference at every step. So let's have a look at that, shall we? Alright, so say that we have some point xi, si, all the way from I equals 0 to n, like we did before. And now we want to compute the difference between every nodes. So the difference between them is h, that's the step size. And we can actually write down a simple function for every finite difference approximated derivative at these points, which will be si plus 1 minus si divided by h. And you can check if this is correct, because when you think about it, the SI is defined as the function that we had, or this is the sine we're dealing with right now, so we might as well write that down at every point xi. So si plus 1 would be equal to sine xi plus h, which is what we have there. So it all works out. What we have not done though is that we have not defined the derivative at the end point. We don't have an expression for Sn plus 1 because our last point is Sn. It doesn't go any longer than that. However, we can also define the derivative function backwards, like this. So we can approximate derivative like so. F of x minus, notice the difference, which will be the exact same thing. This alternative approximation is called the backwards difference formula, while our previous expression was known as the forward difference formula. Quite logically. The naming is quite natural, as the forward difference goes forward and the backwards difference goes forward. So what we could do at the end point when we get there is simply define a slightly different function. So our n would be s of n minus Sn minus 1 divided by h, and then would have all the points and hopefully a complete set of points, which will be a discrete representation of the derivative of the function. So let's try to do this now on the computer. Alright, so as always we need to import some stuff. We'll import numpy as np, and we'll also import sys, and I think we want to, and our n, that's our number of the resolution of our mesh, will be an integer, and we'll make this our first argument. Alright, h will go all the way to 2 pi again, I think. 2 times np.pi divided by n. That's our step size, the length between the points. And x will be a linear spacing, linear grid. 0 up to 2 times pi and n plus 1 points. And our function values will be the sine function again. Yep. Our z will be, firstly, we'll just have zeros, the size of, well, the same size as this, these function points. Well, I'll do this with a for loop first, so to make it clear, but it is possible to do, since we are using numpy, vectorize, which will be a bit quicker, where we do the entire operation in one go. But let's write a for loop. So for I in our range all the way, so we'll do all but one point with the forward formula, right? So our zi now would be s of I plus 1 minus s of I divided by h. And then we'll do the last point. So z of minus 1, that's the last one, equal s, the last one there, minus the second to last one divided by h. And that should hopefully be it. And then we will plot, the x's and the c's, but we'll also plot an exact version of it. So we'll call this x fine, and then we'll simply do the same thing, but make sure that we have a lot of points. 1001 should do it. So we'll call this exact, even though it isn't, which will be the cosine of this x fine, and we will insert it into the same plot. whoops, there, x fine and exact, and we will, I think we should label them. So this is the approximation, and we'll call this guy the exact function. All right, and then we need a legend to see which is which. Then we can show. Okay, let's see if that works. So Python discrete 2a, that's where we're at now, and we'll do 10 points. We need to import matplotlib from import pyplot as plt. There we go. I always do this. Sometimes I get dyslexic on the computer. No offense to dyslexic persons, it must be hell. Oh, I am not a very good typer. There we go. I obviously did something wrong. Yes, here I wrote X instead of S. So let's try it again. Same number, same resolution. There you go. So they're similar. Interestingly, we see that they're a bit skewed compared to each other. So let's do more points. 25. And you can see that we are getting closer and closer. So if we were to increase this to 100, yeah, and there is a discernible difference, but it's getting better and better, as you can see. So yeah, quite good. So, in summary, say we have a discrete version of some function f of x on the interval from a to b, and this would be given by some points xi, yi from I equals 0 all the way up to some n, where the xi's are a, the starting value, plus I times age, and the y's are the the function values at these points, where the I is 0, 1, all the way up to n, where n is some number equal to or larger than 1, hopefully a lot larger than 1. And of course the spacing between the nodes is given by age, which will be b minus a divided by n. There we go. A discrete approximation of the derivative of this function f would now be given by a new set of points xi, whoops, xi ci from I equals 0 all the way to n, and now we can compute them either by I plus 1 minus yi divided by the spacing, or alternatively we have yi minus yi minus 1 divided by the spacing. So this is the forward formula and this is the backward formula. So now this collection z will be, these are the same, and this will be a discrete version of the derivative of the function f. And that's about it. Thank you for watching. In the next video we will look at how integration becomes summation, very similarly to how differentiation became differences in this video.